Okay, so before we start some new topics today, let us look again at the problem that I had given you last time for solving. The problem, if you recall, was to compute the value of sine x given the value of x to a certain accuracy, epsilon. And to compute this, you have to use the Taylor series expansion for sine x, which as you know is x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial, etc. So how do we solve this problem? Well, as I said, we'll just keep computing terms of this series one by one and keep adding them to a sum, which will be the final value of sine x. And this is an infinite series, so we'll have to stop the summation when the absolute difference of two consecutive terms becomes less than epsilon. Okay, so before looking at the program, let's try to work out an informal algorithm for doing this. So let's say we'll use these variables. Sin x will carry the sum of the terms, which will finally of course give the value of the sine of x. And let's say term is the most recently computed term, the last computed term in this series that was computed. And let's use the variable prev term for the term prior to the most recent term. So the difference between the two terms is term minus prev term, and the absolute value of that is the difference. So we'll have to keep computing till the value of difference becomes less than epsilon. Now, one thing that you should note in this series is that when I am computing, let's say, x to the power k over k factorial, where k is some odd number, then I don't have to compute x to the power k and k factorial all over again, because if I do that, I'll have to multiply x k times and then also multiply k by k minus 1, k minus 2, etc. up to 1, which is the number of multiplications. Instead of that, we can use the fact that we already know what the previous term was. The previous term that we had computed was x to the power k minus 2 divided by k minus 2 factorial. So if you just multiply this by x twice and divided by k minus 1 times k, that gives us the value for the next term. Okay, so let's now try to write an informal algorithm using these ideas. So the main loop will look something like this. While difference is less than epsilon, so the term that we computed in the previous iteration will become the previous term for this iteration. So previous term will become equal to the current value of term, and new value of term will have to compute. Let's assume that the previous value of term used a value k, that is the term that we had computed earlier was x to the power k over k factorial. Then the new value of term would be minus term into x divided by k plus 1 times k plus 2. This minus comes because if you observe, the terms in the series have alternating signs, plus and minus, and after this the value of k will become k plus 2, it will get incremented by k, and to the value of sin x will add the value of term. And what else do we need to do? Well, we need to update the value of difference. So difference will now be the new value of the difference, which is term minus the previous term. And that's it. At the end of this, the value of sin x is the desired answer. Okay, so let's now look at the C program to do all this. Okay, here then is the C program to compute sin x. Note that we have a big comment up front which says what the program does and how it does it. If you remember, I told you earlier that writing comments in programs is very important because they help us understand programs. Even the person who has himself written the program may need to understand some difficult parts of it and comments help him do that. Okay, before we look at the other things in the program, let's look at the main loop of the program. Here is the main loop, and it's quite the same as what we just discussed. So while the difference is greater than the value of epsilon, that is as long as the desired accuracy is not obtained, we assign previous term is assigned to term, because the most recent computed term will now become previous term, and the new term will be computed, and the new term is computed from the last computed term as minus term times x square divided by k plus 1 times k plus 2. Note that the expression k plus 1 times k plus 2 has to be enclosed in an extra set of brackets. That is because otherwise it will become equivalent to term into x square divided by k plus 1 but multiplied by k plus 2 instead of multiplication by instead of division by k plus 2. That's because really the division and the multiplication operators have the same what is known as precedence, which we'll talk about in detail later on, and essentially they are carried out in the left to right order. But we'll not worry about this. For the time being, let's just put these extra braces here. So the value of sin x gets updated by the value of this new term, just gets added to the old value. K becomes k plus 2. The new difference is term minus previous term. But remember that we want the absolute value of difference. So how do we compute that? That's pretty straightforward. If the value of difference turns out to be less than 0, then we simply change its sign. Okay, let's now look at the initializations that we need to perform to start off this loop. Now, let's assume that we have already read the value of x and epsilon above these statements in the program. I'll show them to you in a minute. So here are the initializations. So we know the first term is x. So therefore we can assign the term to be x, and the initial value of sin x is also x because term is already included in that. The previous term, the one before this, is of course 0. So therefore the value of previous term is initialized to 0. And the value of difference is also x because term is x and previous term is 0. So difference is term minus previous term, which is x. But of course, since x can be negative, so this difference can be negative as well. And so therefore, if difference is less than 0, we change the sign of the difference. And because the current value of term is x to the power 1 divided by 1 factorial, therefore k should be initialized to 1. Okay. Let's now see what else do we need to do. This is the standard set of statements for reading some input. So we want to read the value of x and the value of epsilon. So you prompt enter value for x, read the value of x using scanf %f. Note that since x is going to be a floating point number of type float, so therefore we have to use %f here, and similarly we use %f to read the value of epsilon. Here are the declarations of various variables. X is the input value. Note that in the program I have given a comment for explaining every variable used in the program. This helps in understandability of the program. So x is the value that is going to be input to us. The variable sin x will hold the value of sin of x. So this comment says the sin x will be equal to sin of x. We can't use sin of x with brackets itself as a variable name because remember that variable names cannot contain bracket characters. So just to verify that our answer is correct, we are also going to use the math library function sin x, which is built into the C math library. Just to verify that our answer is correct, we will also compute the value using the sin x function from the math library. So the variable lib sin x is going to contain the value of sin x obtained using the math library sin function. Epsilon, of course, is the desired accuracy. The term and the previous term, we already know what they are. Term is the current term in the Taylor series. Previous term is the previous term in the series. Diff is the difference between term and previous term, actually the absolute value of that. And k is the current power of x. So always term is x to the power k divided by k factorial. Okay. Now, since we are also going to use a math function, namely sin, from the math library, we also have to include, we have another include statement saying hash include math.h. This statement says that we are going to use a function from the math library, namely sine function. Remember that the hash include stdio.h is there in almost every program that we write, because in almost every program that we write we need to use the standard input and output functions. Okay, so after the loop runs and terminates, finally we can print the value of sin x, so the computed value of sine of whatever. So we want to print the actual value of x here. So we just put %f and that will get replaced by the actual value of f, and the actual value is another real number, so therefore another %f, and the corresponding value is sine of x. And here we are computing the same value using the math library function sine. So lib sin x assign sine of x. So this will directly give us the value of sine of x from the math library, and we are also printing this value just to compare that the value that we have computed is correct. Okay, so let's compile this program and see whether it works correctly. One new thing in this command line for compiling the program that you should notice is this -lm that we have used over here. This -lm is required because we have to tell the compiler that we are using a function from the math library, and therefore the math library should be linked along with our program by the compiler. This is not necessary for the standard C library functions such as printf, scanf, etc. that we have been using, because the C compiler always links the standard C library along with every program that it compiles, but that's not true for the math library and many other specialized libraries that we might need to use in our programs. So in the case of math library, for example, we have to, in the program itself, use the include statement that we just saw. In addition, we have to use this -lm flag to tell the compiler that the math library should also be linked with the program. Okay, the program has been compiled. Let's now try to run it. So let's try to give some familiar values for x. We know that sin pi is 0, so let's try to give the value of pi as the value of x. Let's say we want to have an accuracy up to 5 decimal points. So you can see the answer is almost 0, and in fact the math library function has given precisely the same value. Let's try some other values. Let's say pi by 2, sin pi by 2 is 1, the value of pi by 2 is approximately 1.57, and we get precisely 1 this time. Okay, so this program is working. Okay, let's now talk about another couple of types of values that are very useful in programs. The first such values that we'll talk about are characters. By characters, what is meant is really all these alphabets, numerals, and other special symbols, colon, semicolon, full stop, less than, greater than, etc. that you see on the keyboard. One very important capability of a computer is that it can deal with characters also apart from just numbers, and in particular it can deal with strings, which a string is nothing but a sequence of characters. We'll not talk too much about handling of characters in this lecture. We'll leave that to a later lecture. But we want to talk about a little bit about the representation of characters inside the computer. So how, as you know, that every piece of data inside the computer is represented as a sequence of bits, which are nothing but zeros and ones. So the question is, how would characters be represented in binary? And the natural answer is that we simply assign some codes to different characters, let's say integer codes to the various characters, and when you want to store a character in memory, we just store the corresponding integer code. There are several standard codings which have been defined by various bodies, and many such codings are in use. Some of these codings are called ASCII, Unicode, UTF-8, etc., etc. The C programming language that we are using uses the ASCII standard, which essentially is a standard for defining integer codes corresponding to all characters that you can see on the keyboard. So in the ASCII coding, the different characters are assigned codes from 0 to 127. So that means a total of 128 characters can be represented. Only the Roman alphabet is supported. In some of the other coding schemes, for example, in Unicode and UTF-8, you can in fact support characters from many different scripts like Devanagari and many other scripts. So, but we'll be focusing on ASCII for this course because that is what C uses. So here are some examples of ASCII codes. The codes for the characters A to Z are contiguous, one after the other. The code for small a, character small a is 97, that for small z is 122, B is 98, C is 99, and so on. The capital A to capital Z are also one after the other. Capital A is 65, capital B 66, and so on. Capital Z is 90. And similarly, the characters 0 to 9 have the ASCII codes 48 to 57. Note carefully that we should always be careful in distinguishing between the character 0 and the integer 0. The character 0 would be represented by the ASCII code for 0, which is 48, I'm sorry. Whereas the integer 0 would be stored internally just as the 0 in binary, which is all bits set to 0. So therefore, the character 0 and the integer 0 are very, very different. The C-type correct car, which we have already visited in the last lecture, is usually used in programs to store characters that we might be reading from the input, or we might be manipulating these characters and so on. And the reason for using this type char is, remember that the char type is an integer type for which exactly 1 byte is used for storage, which means that numbers from minus 128 to plus 127 can be represented. And since the ASCII code has codes from 0 to 127, any character can be represented using the char type. But in principle, any integer type can be used to hold a character, because ultimately remember that a character is internally stored as an integer, which is the ASCII code for that particular character. And we can of course also use unsigned char, because the range for unsigned char is going to be from 0 to 255. Okay, another important type of values that we'll often need to deal with in our programs are what are known as Boolean values. And Boolean value is nothing but just true or false. We often need to remember just the truth or falsity of some condition in the program. We're going to shortly see an example of a program which uses this notion. So these values, which are just true or false, they're called Boolean values after the famous mathematician called Boole. However, there is no Boolean type in C, and really to store Boolean values, that is to store true or false, what we can do is to use any integer type. Character, integer, long, short, any of them. In the integer representation for Booleans in C, the value 0 denotes false, whereas any non-zero value, which may be negative or positive, denotes true. Okay, so another example problem that we are going to solve today is to find out whether a given integer n, which is greater than 0, is prime or not. So the primality testing problem has been actually a very fascinating problem for mathematicians for a long time, and people have tried to come up with efficient algorithms for solving this problem. And only recently, in fact as recent as last year, this problem was solved in a very efficient fashion. However, those algorithms are fairly complicated. We'll use a very easy algorithm which should be familiar to all of you for solving this problem, and that algorithm follows directly from the definition of primality. You know that a number is prime if and only if it is divisible by no other number other than 1 and itself. So if there is some other factor of n other than 1 and n itself, then n is not a prime. So essentially the idea to find whether n is prime or not, what we need to do is to test whether n has any factor other than 1 and n or not. So we need to test for factors from 2 to n minus 1. However, we don't need to test all these numbers to check whether any of them is a factor of n or not, because you know that if there is a factor of n, let's say p, which is greater than square root of n, then there must be another factor q which is less than square root of n. Why is that? If you take simply q to be n by p, since p is a factor of n, so therefore q must be an integer, that is p evenly divides n, and since p is greater than square root of n and p times q is n, therefore q must be less than square root of n. What does that tell us? That tells us that we need to look for a divisor or a factor of n only from 2 up to square root of n. If we cannot find a factor of n from 2 to square root of n, that means there cannot be any factor greater than square root of n either, apart from n of course itself. Okay, so how do we use these facts to fashion an algorithm? So essential idea is very simple. Let's use a variable called p, which is the potential factor that we are going to test whether it's a factor of n or not. How do we test whether p is a factor of n or not? We just have to check the remainder of the division of n by p and test whether the remainder is 0 or not. So if p is a factor, then the remainder would be 0. And in C there is an operator called the percent operator, which does precisely that. So n percent p will give us exactly the value of the remainder when n is divided by p. So if n percent p is equal to 0, this implies that p is a factor of n. Okay, so what we need to do is to have a loop, run a loop from 2 to square root of n, and so p will vary from 2 to square root of n in that loop, and if at any step p is a factor of n, then we should stop the loop. So the loop will look like this while some condition. If the remainder obtained by dividing n by p is 0, then we know that n is not a prime. Indeed, p is a factor of n, which is other than 1 and n itself. Then we need to do something. Then we need to in fact stop the loop. Otherwise, we just have to increment p by p plus 1. I have put a question mark here because we don't really know what we need to write here. Okay, so the question really is how long this loop should run. Now clearly, this loop has to stop as soon as the value of p becomes greater than square root of n. So therefore, it must be running only as long as p is less than or equal to square root of n. But if we find one factor of p, one factor of n, then we don't need to test the further integers up to square root of n, because finding one factor of n is good enough to say that n is not a prime. So therefore, we must stop the loop as soon as we find a factor, if we find a factor. If we don't find a factor, then of course the loop will terminate when ultimately p becomes greater than square root of n. It will finally become greater than square root of n because in every iteration we are incrementing p by 1. So now we need to, in this case, remember the truth or falsity of the condition, that is n percent p is equal to 0 or not. So let's use a Boolean variable to store this value. Let's call that Boolean variable as found. So found will be either true or false. So we'll start out as false. So true will be initialized to false, and found will be initialized to false and will become true as soon as we find one factor of n. So therefore, it should be set to true whenever we find that n percent p has become equal to 0. So this question mark should now be replaced with found sine true, and this condition which we still have not completed. So we must keep running the loop as long as p is less than equal to n, less than equal to square root of n, and we have not found a factor, right? Because as soon as we find a factor, we should terminate the loop. Okay. So this is the basic idea of the algorithm. Note that we have used a Boolean variable found here, which of course in the C program, as we have just seen, will be represented using a variable of type int only, because there are no Boolean types in C. And we have also used two operations on Boolean values, and not. So the operation not essentially inverts the truth value. So that is, if the value is true, not of that value is false, and vice versa. So if the value of found is true, then not found is false, and similarly if the value of found is false, then not found is true. And the operator AND is a binary operator, that is, it has two operands. So in this example, here are the two operands, p less than equal to square root n and not found. So essentially what the AND operator does is that it gives the value true if both the operands have the value true, right? So if p is less than square root of n, less than equal to square root of n, and not found is true, meaning that found is false, then this entire expression will have the value true. And therefore, if that is the case, then this loop will continue. Whereas, if either of these two conditions is false, that is, either p becomes greater than square root of n, in which case we should terminate the loop, because we have not been able to find any factor and we have tested all possible factors from 2 to square root of n. Or if we have found a factor, then also we should terminate the loop, because we know now that n is not a prime and p is a factor for n. So if found is true, then not found is false, and since and gives the value true only if both the operands are true, it will give the value false, and therefore the loop will terminate. So let's now convert these ideas into a C program. Okay, so here is the program based on the algorithm that we just discussed. So it starts out with a comment as usual saying what the program does. So it finds whether a non-negative integer is prime or not by trying to find a factor for it. We have to include the stdio.h file as usual. Math.h we have included because we are going to use the square root function from the math library. Okay, so as you know now that the C language does not define any Boolean types. We use integer type for Booleans as well. So we are going to use the value 1 to represent true and 0 to represent false. Recall that every non-zero value is considered true and 0 is false. So it is usually a convention to use 1 as the value for true. And here is one more way of defining constants in the program. In the program that we had written in the last lecture for computing the area of a circle, we had defined constants by declaring them as variables but prefixing the declaration with the word const. This is one more way. So if you say hash defined true 1 and hash defined false 0, what this essentially means is that in the rest of the program, wherever the word true or the word false appears, that will be replaced by the value 0 or by the value 1 as the case might be. Okay, so here is the main program. This time we are using slightly different types. We are using the type unsigned long for n, so that n can be as big as we can manage, as big as we can handle. N has to be always non-negative, so therefore we can make it unsigned. Similarly, potential divisor is unsigned long, and the initial value for potential divisor is 2. So this potential divisor is the variable p that we had been using in the algorithm. So in the program, we are using more verbose names for variables, longer names for variables, so that we know precisely what a variable stands for and what is the function that it is performing in the program. And the variable found that we were using in the algorithm is called found a divisor in this particular program, and it precisely, so as you can see, the name precisely specifies or indicates exactly what is meant by this variable, what is the purpose of this variable. Now this has to be conceptually, if it is of type Boolean, because it will only hold a true or false value. So but in C we have to use some integer type for this variable. So we have used the type char. We could have used any integer type, but we have used the type char because the type char requires the least amount of storage among the integer types. So using the type char for representing Boolean variables is a good practice, because the program doesn't in that case use unnecessary storage. And of course we just need to represent the values 0 and 1, so char type is good enough. Now max try is going to be the value of square root of n, or in fact the integer which is just below the square root of n. In other words, max try is going to be the floor of square root of n. Note that the square root of n need not be an integer. For example, if n is 10, then the square root of 10 is 3 point something. So in that case, max try should be 3. We don't need to test for any divisor above 3, because if there is a divisor above 3, then there will be a divisor below 3 as well. Okay, so here is the starting of the program. We read the number as usual after entering a prompt, and straight away we compute the square root of n by using the square root function in the math library. The square root function actually gives a double value, and we are assigning this double value to a variable of type unsigned long. Remember that max try is unsigned long. So here the compiler automatically converts this double value to an unsigned long value. This is called implicit type conversion, which will not talk in too much detail in this lecture. We'll talk about it later, but intuitively what is happening here is that out of the double value, when it is converted to an unsigned long integer, the fractional part of the real number will be chopped off and only the integer part will be retained. So here is the main loop, pretty much what we saw in the algorithm. The condition for the while loop is while potential divisor is less than equal to max try, and so this pair of these two ampersands denote the AND logical or Boolean operation in C, and this band character or the exclamation mark denotes the negation Boolean operation, or the not Boolean operation in C. So the loop condition is while potential divisor is less than equal to max try and we have not so far found a divisor. Note that the loop will terminate when either potential divisor becomes greater than max try or we find the divisor. So if n% potential divisor is 0, then founded divisor is set to true. Otherwise, potential divisor is simply incremented by 1. Note that the body of the while loop is a single if-else statement. So this entire thing is a single if-else statement, and therefore we don't need braces around the body of the while loop because it is just one statement. And similarly, the then part of the if statement is a single assignment statement, so we don't need braces here. And the else part is also a single assignment statement, so we don't need braces around this either. Though of course if we put braces, there is no problem with that. So this is the end of the loop. At the end, when the loop terminates, if we have found a divisor, that means that n is not a prime. So in fact, instead of just saying n is not a prime, we also say that n is not a prime because here is a factor of n which is not 1 and which is not n. So %d is a factor of %d. The first %d is replaced by potential divisor, which of course is the actual divisor that we found, or the actual factor that we found, and this %d will of course be replaced by the value of n. If the variable found a divisor is false, then we print that the given number n is a prime. So it's a pretty straightforward program. Let's now try to compile this and see whether it works correctly. Again, we have to use the -lm flag to compile this program because we are using the square root function from the math library, and if you remember, we had also included math.h in the program file itself. Okay, so let's now just execute this program. Let's try with some non-prime number. Let's say 16. 2 is a factor of 16. Let's try with a larger number, 324. Of course, 2 will again be a factor. So let's try 327. This time 3 is a factor. 2 is of course a factor. Let's try with some prime numbers. 17 is a prime. 19 is a prime. 23 is a prime, and so on. So the program is working correctly. So this brings us to the end of this lecture. In the next lecture, we'll start talking about operators in C of various kinds. We'll start with arithmetic operators and then talk about other different kinds of operators like Boolean operators, etc. in more detail, and we'll see how complicated expressions can be formed out of by using and combining these different operators in various ways. We've already been using these operators in the programs that we have been writing, but we'll discuss them more formally in the next lecture and also discuss some of the subtle details associated with these operators.